Hello everyone and welcome to episode 3 of Particles in a Box. Today we are going to be talking about limits, derivatives, and series. So this is going to be our first quote-unquote pure math episode. Where we're not going to be doing a whole lot of physics in this. It's mostly about doing the math and a little bit of the theory behind the math. Some people like to say that physics is applied math, and in some ways, I think that's true. I'm definitely the sort of person where part of the reason why I like physics is because you're applying it to real world scenarios, and so when you get bogged down into the theoretical math, and some of the proofs and technicalities, I don't particularly always enjoy that, but I do recognize that they are important. So with that in mind, down here at the bottom. We got a little bit of a meme here. It's called going off on a tangent because it's a derivative of the original conversation. I remember the first time that I saw this in Calc 1 and it was like, oh my gosh, that is actually so true. It's one of those like realizations like, oh my gosh, this is actually, it actually makes a whole lot of sense. So hopefully by the end of this, you'll understand more about this meme. And with that being said, I've got our overview here. So first off, we're going to talk about limits. What is a limit? How do we evaluate limits? Why are limits useful? And then we'll move into derivatives. So there's the definition of the derivative, like the fundamental like definition mathematically of what a derivative is. Then we got the power rule and the chain rule, which are two very useful formulas for finding derivatives. Then there are some other rules that we'll also go over. And then we'll talk about partial derivatives, the gradient, the directional derivative, and the total derivative. Those four are multivariable derivatives, where they deal with functions of more than one variable. So we'll briefly talk about those, even though we won't be using them a whole lot until later on in future episodes of the show. And then we'll quickly talk about series. We'll talk about Taylor series, we'll talk about convergence, and then we'll briefly mention Fourier series as well. So before I get too far in the video, I do want to give a massive warning here. This is not meant to replace your AP Calculus A, B, B, C, or your college calc classes 1, 2, or 3. Okay, this is purely meant as more of an overview. And since I use calculus in a lot of my derivations and in a lot of the problems and the physics topics that we use, right, I'm trying to get those of you that don't have a whole lot of familiarity in calculus somewhat up to speed, so that way you can at least understand the concept of what a derivative is and what a limit is and what a series is, right? Even though you may not have done like the rigor of like a Calc 1 class, right? I still highly recommend that you take the class itself because you'll get in the reps, you'll get the experience of doing these over and over and over again. And having that experience and having that intuition as you go forward is going to be really helpful to you. So definitely don't downplay the value of taking a full calculus class, because you will learn a lot more in that class than you will for this video. Okay, so with that being said, our first topic is limits. So first of all, we have the formal epsilon delta definition of what a limit is. Okay, so f of x has the limit L as x approaches a if for any positive number epsilon, however small, we can find some positive number delta such that the absolute value of the function f of x minus L is less than epsilon if 0 is less than the absolute value of x minus a, which is less than delta. And write that the limit as x goes to a of f of x is equal to L. So what in the world does this actually mean? Well, first of all, I will tell you that if you aren't in a math class, like an actual like math class that's like proofs based, or is like a calculus class of some sort, you will almost never use this. In physics, most of the time we don't need to use this definition to evaluate a limit. So I'm just kind of going to throw this up here because this is the formal definition. But if you want more in depth on how to actually apply this, go take a math class. Is my best advice for you. Because it's a lot of verbatim, and I remember taking my intro to analysis class, and I did not like I did not like doing this. So yeah. So then down here on the bottom left, we have just some limit rules. Most of them are relatively intuitive, right? is that if you have two functions and you take the limit, right, you can add their limits. Difference rule, you can multiply by a constant, right? The product rule applies. You got the quotient rule, the power rule, and the root rule, right? So limits work like how you want them to, right? There isn't too many tricky things about them. Okay, so limits and continuity. What you can do is that you can have have like a subset of a limit, right? So you can have a right-hand limit and you can have a left-hand limit. So what do I mean by that? Well, if you take the function, the absolute value of x over x, right? The function looks something like this, right? You have your 1 up here and you have your negative 1 down here, right? But if you approach from the right to x equals 0, right, and you approach in from the right, you're going to get a value of 1, right there. But if you come in from the left, right, you're going to get a value of negative 1, okay? You know, again, it kind of depends on the function that you're dealing with, right? Like the absolute value of x over x, right, it is a good example of this. Another example could be 1 over x, right? That's 1 over x does something like that, right? So if you're coming in from the left, right, you're going to get negative infinity. If you're coming in from the right, you're going to get positive infinity. So if you have like a discontinuity or like a vertical asymptote, right, these left and right hand limits can be really useful. It's also useful for telling you if a limit at a value itself exists, right? So if the limits from your two directions differ, then the limit at that point technically does not exist, right? So if we go back to our absolute value example, right, if you just evaluate the limit at x equals 0, well, there's a discontinuity right here, so you can't actually evaluate that, right? It does not exist. And then a quick mention about continuity is that some people have a misconception that if there's a derivative, it's continuous, and that is actually not true. It has to do with limits. And so if f of x is defined at a, right, then the function's continuous there. If the limit as x goes to a of f of x exists at that point, and you need the value of the function to be the limit. An example of when this isn't actually true is of sine of x over x. Okay, the limit does exist. It is 1, but if you actually graph it, there's going to be a hole. Because you're dividing by 0, right, with the x, right? So there's going to be a hole there, right? So technically, the limit does not equal the value of the function, right? Like there is no value of the function at x equals 0. So the function would not be continuous at x equals 0. So how do we? So why are limits useful? Well, as you can tell, when we talk about derivatives, the limit is going to come up in its definition. But it's just a nice tool to tell us, do functions approach certain values? It gives us the definition of continuity, right? And then it's going to come from the derivative. When we do a couple of examples, you'll see a little bit more about how we evaluate them and how they can potentially be useful. I guess a couple more things, right, is that this limit sine of x over x is a very common limit. You can use this limit to evaluate a lot of other limits. I'm not going to show a formal proof here of why this is true, but it is. As Mathematica has shown us here. And then I've got another limit here, just 1 plus the hyperbolic sine over e to the x as x goes to infinity. That limit just happens to be 1/2, right? And then I have a bunch of the absolute value over x limits down here. Like as you're just starting out, right, they're going to have you, if you're in Calc 1 or in Calc AB or something like that, right, they're going to have you evaluate limits by hand. But as you get farther and farther along in your mathematical career, they don't want you to be using your time up on evaluating limits. They trust that, hey, you've done this before, go ahead and plug it into a computer and move along to more important stuff. Yeah. All right, so derivatives. Derivatives are a huge concept in physics. You know, we use them all the time, be it in differential equations or just using them quickly to find a slope, a tangent to a graph, or there's just so many applications as to what a derivative can be used for. So first of all, the definition. So the derivative at a point A, also denoted as f prime of A, is equal to the limit as h goes to 0 of the function evaluated at point A plus h minus f of A over h. Okay, so that's just the formal definition. So for a function f of x, the first derivative with respect to x can be written as one of the following. So you can have df of x over dx. So sort of written in a fraction notation, right? Sometimes you'll also see dy dx, right, for example. You can write it as f prime of x, or you can write it as a capital D subscript x, f of x. Each of these have their own uses, right? It kind of depends on the situation, depends on which one of these you want to use. The most useful one, in my opinion, is the fraction one, because you can do cheeky things where you like multiply by a dx dy, for example, and you get 1. Right, because you can cancel out like the numerators of stuff and the denominators of stuff to get something new, as you'll see here in a little bit. So the fraction one is pretty nice to use. Sometimes if you're just not wanting to write out the whole fraction, right, f prime is used. This one is more of a multivariable derivative thing, right, where you can change the subscript to a y, for example, like dy f of x, right, and you can get something different. This one isn't used a whole lot, but it is still worth. Okay, so unit a note about units, right, is that if you have a graph y and x, right, whatever the units of y are over the units of whatever x are is equal to the units of whatever your derivative is. So common ones that you'll see, right, is if you have like seconds down here, right, and you have meters, right, then your derivative is meters per second, which is velocity, right? So, you know, that's one common example of a derivative. Let's see. So before we go on to the next slide here, right? Like, okay, so there's this definition, but what does it look like visually, right? Having the visual representation, it really helps out with what derivative is here, right? So I'm going to pull over good old Mathematica here, and so what we got here, just to explain what's going on here a little bit, right? Is I defined a function here, right? And this function, what it does, it takes in a function. The variable is x, and it uses a point, or in other words, an x coordinate of p. Okay, so general variable x, and then a specific x coordinate p, right? And so that's equal to the derivative evaluated at p times x minus p plus f of p. Okay. In my last video, I mentioned point slope form, right? So point slope form is mx minus x1 is equal to y minus y1, right? So if we're taking a look at what I just had on the Mathematica screen, right, we had an f prime of p, which is just absolutely written terribly. Okay, that is m. Okay, and then we had an x minus p, where p is x1 plus a f of p, and f of p is just y1. Okay, so we added the y1 over to the other side, and then we have some function that's equal to y. Whoops. Let's see. Back. Okay, there we go. So, so what I did is that you have some function q is equal to e to this checkerboard. Checkerboard is just like a placeholder, right? Because down here you end up putting in x, x for that. So the blue line here, right, is the curve e to the x, right? And then this orange line is the tangent line to the blue curve at this red point, okay? And so what the derivative does is it tells you the slope of what this line is, okay, of what this orange line is. So as we move the point, the line is going to get steeper and steeper, right? And so the derivative is just whatever the slope of this orange line is, okay? And you can evaluate that at points along the curve, okay? What happens if I change the function, say to x squared, right? Okay, well, now we start off with a negative 1, right? At 0, it's 0, so it's just a flat line, and then it increases, okay? You can even do this for trigonomic functions, right? Right, so that the function goes up and goes down, right? So that's what the visualization of a derivative is, right? It's just that it's this, whatever this line is, it is the slope of that line. And that is an incredibly useful useful tool, as it turns out. So how do you actually find a derivative? Okay. Well, as you know, there are some different like categories of functions that are commonly used, right? There's the trigonomic functions like sine and cosine. There's the exponential function e to the x. And then there's like polynomials. And then there's obviously like some other special functions and whatnot that you can kind of address on a case-by-case basis. So one of the big ones, obviously, right, is a polynomial. So how do I take the derivative of a polynomial, right? So our function is equal to x to some power, right? Where n is some positive integer, right? So you can have x to the 0, you can have x to the first, right, which is a linear line. You can have x squared, which is a quadratic. You can have x cubed, which is a cubic, right? So what we do, right, is that we start off with, we want to figure out what f prime of x is. So that's equal to the definition of the limit, definition of the derivative, which is the limit as h goes to 0 of the function x plus h minus f of x over h. So we can go ahead and plug in our function here. Remember, x plus h means you substitute for x, you substitute in x plus h. So it's x plus h to the n minus x to the n. So what you can do is that if you're familiar with binomial expansion theorem, you can expand any factor to the n power, and you get out something that's going to look like this, right? Minus x to the n over h. Turns out, right, that you have an x to the n here, and you have an x to the n here, right? And you can subtract, and so those are going to cancel out, right? And then you end up with this over here, right? And so all of these terms have an h in them, so you can cancel out h's out of all these terms. And when you cancel out all the h's, you get something like this, right? This first term, you now notice, does not have an h in it. All the rest of them do. So since all the other terms have an h in them, all of these other terms are going to go to 0 when we evaluate the limit. And we end up with nx to the n minus 1, okay? So this is the power rule. So any polynomial function, right, you can take this is the derivative of that function, right? So x squared, right? If you take the derivative, you get 1/2 x. I mean, whoops, you do not get 1/2 x. Oh my gosh, that is embarrassing. It's 2x, right? So you drop down the power, and then you subtract 1 off of it, right? So when you drop down the power, you're going to get 2, and then you take 1 off of it, right? You get this, right? If you have an x to the 4th, right, it's going to be 4x cubed, okay? And since you can add, so like if you had an x squared plus 4x, for example, right? If you want to take the derivative of this, right, you can take the derivative of the first part, x squared, 2x, and then add it to the derivative of this part, which is 4. So you get 2x plus 4. Okay, so that's just the power rule. One of the most common, one of the most common rules that you use, because you deal with polynomials quite a bit. This particular proof relies on n being a positive integer. We're going to do one a little bit later in the video that doesn't make this requirement. But by other means, it can prove that the rule applies to negative and fractional powers. So 1 over x, right? You can take the derivative of this, right? It can be written as x to the negative first. So if you take the derivative of this, you get negative x to the negative second, which is negative 1 over x squared, right? So you can do that. You can also do the square root of x, right? So x is equal to the 1/2. So you drop down the power, that's 1/2. And then 1/2 minus 1, you get negative 1/2. So this would be 1 over 2 square root x. And so that's the derivative of the square root, okay? So we want to use, so we're going to go back to the definition of the derivative here to derive some other common derivatives, right? We just show that we can take the derivative of any polynomial function, and we now know what the derivative of that is. But what about e to the x, okay? How do you take the derivative of an exponential function? Start with our definition of the derivative. We plug in our x plus h and our x's, okay? By using exponent rules, you can split the e to the x and the e to the h, right? You can then factor out the e to the x and pull the e to the x out front, which we do right here. And so then what we do is we do a little bit of a substitution, okay? We're going to allow n to equal e to the h minus 1, okay? The key reason why you can do this is because the limit as n goes to 0 is equal to the limit as h goes to 0 of this expression, okay? Right, so if n is 0, right, you get 0, okay? If you plug in 0 for h, this goes to 1, and then a 1 minus 1 is equal to 0. So you get 0 is equal to 0 when you evaluate those using, as each variable goes to 0. So that's why you're allowed to do that. So what that allows us to do, right, is that you can rearrange this expression itself for h. You're going to get natural log of x plus 1 on the bottom, and you're going to get n on the top, okay? You can pull the e to the x out front because there is no n in e to the x, right? It's treated basically as a constant is basically what it's being treated as because the e to the x does not depend on n. So anything that doesn't involve your variable that you're approximating to, you can pull it out front if you can factor it out, okay? So then what we're going to do is we're going to multiply by a fancy 1 here, okay? So what do I mean by fancy 1? We're going to multiply by 1 over the n over 1 over n, okay? This is a pretty common trick, right? Where you multiply, because this is really equal to 1, right? It's just written in a weird way. But it's a nice little trick because what it allows us to do is it allows us to get our numerator equal to 1. And then it also allows us to make the bottom a lot nicer. I just realized I made a mistake that this should be n, by the way. That should not be x. So my bad about that. So that should be an n. So we get so we multiply by 1 over n, right? You would get 1 over n natural log of an n plus 1. Right, and then using log rules, you can plunk that into your natural log as an exponent. Okay. The reason why this is useful is because we know that the value of e itself is equal to this limit. Okay, that's just a definition of e, and so you can see that definition is in there. So what we end up getting is you get the natural log of e. The natural log of e is just 1, so we get that the derivative of e to the x is e to the x. Okay. This is extremely important. You'll use this a lot when you're doing derivatives. It's an interesting result, suffice to say, but it's a very important one. So this is definitely one that you want to have memorized. You want to know that e to the x is equal to e to the x. The derivative is equal to e to the x. So yeah. So the next, so now we have exponentials and we have polynomials. What about trigonomic functions, right? So we have f of x is equal to sine of x, right? We're going to plug that into our formula, right? So you're going to get sine of x plus h minus sine of x over h. What we're going to do is that this right here, you're adding things together inside the sign. So there's a trigonomic identity that you can use. That trigonomic identity is going to give you this expression right here, minus sine of x. So what you can do is that if you go back to our very first slide, way back at the beginning, right? You can add you can add limits. You can change this expression so that you split it into two different limits. So you can take the cosine part here, right, and make that one limit, and then you can take this second part and make it another limit, and you can add them together. Okay. So the reason why this is useful, right, is that, well, this is cosine of x. There is no x here in the limit, so you can just pop that out front. Here, right, sine of x, there's no x dependent, so you can factor out a sine of x. So that's what we end up getting this down here. Then here, right, we get the same thing. We just go straight down. Here we multiply by -1. So we multiplied this whole part by -1. So we get the minus sign out here now. And then that changes the order of the subtraction in here. And so it turns out, right, that the sine of h over h, as h goes to 0, that limit is 1. Okay, so this limit here is going to 1. And then the limit as 1 minus cosine of x or h over h as h goes to 0 is equal to 0. So this whole thing is going to go to 0. So what that means is that this whole term gets eliminated out here. And since this inner part, this limit part goes to 1, we're left with a cosine of x. So the derivative of sine x is cosine of x. That is also a very big deal. That is also very nice. So you take the derivative of sine, you get to cosine. So what happens if you need to take the derivative of cosine? You might be asking. Okay, well, we basically go along and we do the same process, right? We split things into different limits, right? We factor out certain things, right? You get that this part goes to 0, right? This part goes to 1. And so this whole term out here gets eliminated, and we're left with just the negative sine x. So the derivative of cosine is negative sine x. So what does this mean? Well, say we start out with sine of x, right? As our function, right? F of x equal to sine of x. The first derivative is going to be cosine of x. Okay, that is going to be f prime of x. The second derivative is going to be negative sine of x. Okay, and then if you take the next derivative, you're going to get negative cosine of x. Okay, and then if you take the derivative again, you're going to be back to sine of x. So you go from sine of x to cosine of x to negative sine x to negative cosine x back to sine of x. So it's just a continuous cycle as you take derivatives of sine and cosine. It just cycles, which is intriguing. Honestly, it's an interesting property. So yeah, just a neat little result. So that's now exponential, polynomial, and trigonometric functions that we've got. So then we got another type of function, right? The natural log of x. Okay. So logarithmic functions. Okay. So what we're going to be doing is that, again, right, we're going to be applying our stuff here. You can use a log property to get this x on the bottom, as you can see right here. And then you can simplify inside, right? X over x is 1, h over x, and you can write this h as 1 over h. The reason why you want to write this as 1 over h is, again, you can use a log property so that you can pull that inside the natural log, and you can plop that in up there, right? Again, we're going to let n equal h over x, right? The limit as n goes to 0 is equal to 0 of this expression, right? And the limit as h goes to 0 of this expression, right, is also equal to 0. So we can do that substitution. That's totally valid. So what you end up getting is that you get 1 plus n to the 1 over n times x power, right? You can rewrite this again, right? Because if you multiply powers, right, you can raise it to a power. So that's why you get this really interesting looking thing: 1 plus n to the 1 over n power to the 1 over x power, all inside the natural log. And so what that allows us to do is it allows us to pull out the 1 over x out front, and since it doesn't depend on n, we can pull it out in front of the limit. And then if you remember from our e to the x slide, right? You can you can use that definition. And so when you end up taking the natural log, right? I actually made a mistake here, believe it or not. Yeah, I definitely made a mistake. So there should not be an n right here. And so this n goes away. So this actually becomes a 1 right here. So the limit as n goes to 0 of 1 is equal to 1 over x. So you end up getting that that 1 over x, that the derivative of natural log is 1 over x. Okay. So that is also quite interesting in that if you have your original function, the natural log of x, right, and you take the derivative, right, you're going to get 1 over x. Okay, and then if you take the derivative of that, you can go back to our power rule, and you get negative 1 over x squared, right? And so you can go from a logarithmic function to a polynomial to a bunch of successive series of polynomials as you work your way down. And so that's again a powerful result. Okay. So tangent line, I guess I already went over this a little bit, right? But like, what's the visual representation of a derivative? Right, is you have a tangent line at some points, and the slope of that line is equal to the derivative. Again, that visual representation is just super powerful and is super important. So our next rule. Our next rule is called the chain rule. So if you have a composite function, f of g of x, right, the derivative is equal to the outer function with respect to the inner function times the inner function with respect to your variable. So that's a lot of weird notation. So what does this actually look like, right? So this is how I personally do it, right? Other people have different ways of like laying this out, right? But if you look at this, right, our outer function is natural log, and our inner function is this linear term, right? So the inner function, f of x minus 3, and our outer function is the natural log of whatever the inner function is, okay? So you make a quick substitution for this inner part. And so what that allows you to do is it allows you to take the derivative of I with respect to x, right? So you're doing this part right here. And so the derivative of 4x minus 3 is 4, based off of our power rule. And then you can take the derivative of the outer function with respect to the inner function. So that's what we're doing. So from up here, right, this weird looking thing is actually this. And so we note the derivative of natural log is 1 over the inside, okay? And so then what you do is you do your outer times your inner, and then you replace whatever your inner was. So you have to plug in whatever your substitution was back in. And so you would get the derivative of the natural log of 4x minus 3. The derivative of that is 4 over 4x minus 3. Okay, so that's just an example of the chain rule in practice. You'll use the chain rule a lot, right? it's very useful. Again, take a calculus class, get in the reps, see all the weird, nasty functions that they throw at you, and you'll get good at doing this, at doing the chain rule pretty fast. So other rules. So if you have an addition of functions, right, you just add the derivatives. When you have a constant, the derivative of that is equal to 0. I like with the power rule, right, nx to the n minus 1. If you have x to the, if you have x to the 0, right, well, you drop down the 0, and yeah, and you don't get, and even if you got, sorry, it'd be 0 times x to the negative 1. Okay, well, you're still multiplying by 0, so you're going to get 0. Right, so the constant, if you have the derivative of a constant, it's 0. The coefficient rule, right, is that you can just pull out the coefficient, and then you just get c times that. One that is super useful, though, is the product rule, where if you multiply two functions together, you do the derivative of the first times the second function plus the first function times the derivative of the second. Okay. So that is so that's very useful. And from this you can get the quotient rule, okay, where you get f of x over g of x. If you take the derivative of that, you're gonna get this thing. So you get the the low function, d high, the derivative of the high function or the numerator, plus high, the original function in the numerator, d low, which is the derivative of the low function, all over low squared below. Okay. Most of the time, this squared, it really sucks. To be honest, you try to, if you have something that's f of x over g of x, you try to get it in a product rule form so you could use that instead. As that is definitely easier, as it's just doing half the work of the quotient rule. But you can do it either way. So again, those are quite useful, especially the product rule and quotient rule when you're multiplying functions together. Yeah, it can get complicated real fast in some of these examples. So the next thing is called implicit differentiation. Okay. So if you remember from last episode, I had a problem dealing with two balls and a rod, and the two balls were connected by a rod, and one of the balls was moving, so it was like, how fast did the other ball move? But we're going to take a look at this from the mathematical standpoint, right? So how I did it originally, right, is we had a function a squared plus b squared is equal to L. I solved for b. I took the derivative with respect to time. Okay, so we got dB dt, right, is equal to is equal to this is equal to this here, right? And I went through and I used the chain rule. Right, we had the square root of an L squared minus a squared, so our inner function was the L squared minus a squared, and our outer function was just the square root of whatever was inside. And so you go through, you take the derivative of that, right? You get minus 2a dA dt. So the reason why it's not just minus 2a is because we are implicitly differentiating this, right? In that this a is really equal to a of t, okay? This a is dependent on another variable t, okay? And that is one thing that I do kind of hate about math sometimes, is that they write a function, right? They'll just say you have a, is that like you have a function, right? And then they do some like operations on it, but then you end up scratching your head. Well, wait a second. Was this a function of x? Was this a function of x and y? Was this a function of x, y, and z? Was this like some parameterized function where like the y depended on t, right? Like there's so many like categories of functions, right? That it can be hard to keep things straight. So yeah, it can get complicated. But again, right? If you need to write it out, be like, okay, a depends on t, so I'm going to write it a as a function of t, right? So that's why when you take the derivative of L squared minus A squared, right? You do it like normal, right? So you get the minus 2, you get the minus 2A, right? But then you add on the derivative, okay? Sometimes just adding on the derivative like this can get you in trouble, but most of the time you're not going to have like a square derivative or anything too weird. But you definitely do want to be careful. Again, take a calculus class, do the reps. They'll get you some weird scenario where it's like, oh wait, this part actually has to be squared or something. It's pretty rare that happens, but again, this is why having the experience is important. But anyways, moving on, we have the derivative of the outside, 1 over 2 square root of the inside. And you end up getting out this big thing, and then you ended up canceling out the 2's, right? And you end up plugging, so then you end up finding the complete derivative, right? And then we know that the derivative of something with respect to time is the velocity, right? And then we knew that a over that was equal to the cotangent, because this was b, right? B was that. But there's another way I could have done it, right? In that we have a function of a we had a squared plus b squared is equal to L squared, right? Same thing over here, right? I just wrote it out using function notation, right? Because a and b depend on t, and then I just implicitly differentiate both of them, right? So you get 2a dA dt, but again, b, right, is also dependent on t, right? So you need to include the dB dt, and then the derivative of a constant is 0. And so then you can quickly solve, and you can get this, right? And then you can know that cotangent of theta is a over b, and so then you get the same thing that we did before, and we didn't have to go through this whole chain rule process, right? We could just do it right away. So if you have, so like this is useful, right? Like if you have a function of like a circle, right? You have x squared plus y squared is equal to the radius squared, right? And you need to find the derivative, right? Well, this is 2x prime plus 2y y prime is equal to 0, right? And you can solve for things quickly off of that, right? Without having to solve for y and getting y is equal to like the square root of r squared minus x squared, right? Like it's annoying to deal with square roots, right? Because you're going to have to end up using the chain rule, right? So try to save yourself some work and some time if you can. Let's see another rule here. Not the last rule, but another kind of niche rule. You don't use this one very often, but it is important in deriving some derivatives, right? Is logarithmic differentiation. So, for example, if you have the function x to the x, right? What is the derivative, right? You might think, well, I can just use the power rule, right? Well, this isn't a constant. This is not a number, right? So since the exponent is not a number, you can't use the power rule. So what you can do is you can take the natural log of both sides, and then you can use a exponent rule to get the x out front. Then you can implicitly differentiate, like what we did in the previous slide, right? So the derivative of natural log y is 1 over y, but you have to add in the y prime. So because y is a function of x, okay? So we're taking dy, we're trying to find dy dx. So since y is dependent on x, we need to add in this y prime. And we also have the natural log of y is equal to something, right? It's not y is equal to something, it's the natural log of y is equal to something, right? So the only time that you don't have to add the y prime here, right, is if you have y is equal to some function of x, straight up, right? So yeah, when you have to implicitly differentiate, right, it's kind of on a case-by-case basis. Again, take a calculus class, do the reps. They'll show you when this is applicable and when it isn't. So keep going with that. So you get y over y prime, and then what you have to do is you have to do the product rule here. So x natural log of x, right? So you do the derivative of the first, which is 1, times the second function, which is natural log x, plus the derivative of the second, which is 1 over x, times the first function, which is x, okay? And then when that simplifies down, right, you get natural log of x plus 1. and then you solve for y prime, and you get y prime is equal to y, natural log x plus 1, and then you have to plug in your original thing for y, okay? So yeah, so that's the derivative of x dx. It's x dx times the quantity natural log of x plus 1. So there you go. But what we can do is that we can take that logarithmic differentiation and that implicit differentiation, and we can derive a better expression for the power rule, right? In our first one, right, we used the binomial expansion theorem. So the exponent n had to be a positive real integer, okay? But now you can, but using this method, you can prove it for any real number, right? So now you can do negative numbers, right? Which I already showed you, right? You can do 1 over x is negative 1 over x squared, for example, right? So it expands the power of the power rule, I guess, if you want to say it that way. So it's a very similar proof as to what we did before, right? Keep in mind that n is a constant, right? So you can just do 1 over x times n, right? And you go through and you end up getting this right here, right? But then x over n over x, right? You subtract the exponents and you get our good old power rule. That is so powerful. Yay, woo, okay. So it works for any real number, which is very nice. So need to know derivatives. The derivatives that are on this slide are ones I would recommend you memorize, just straight up. If you want a proof of any of these, they're definitely out there. You can go look them up for yourself. But these are ones that you kind of just want to be able to know off the top of your head. So yeah, when you do integration, which is going to be the next episode, by the way, knowing these by heart is going to save you a lot of time and effort. And when you're doing differential equations, this is going to save you a lot of time. It's just good to have these in your back pocket so you can whip them out whenever you need to. So the last thing before we move on to multivariable derivatives is L'Hopital's rule. Okay. So L'Hopital's rule uses derivatives, which is why this isn't on the limit slide in the limit section. And so what it is that if you have a limit, right, and you have some function on the top and some function on the bottom, you can evaluate that limit by taking the derivative of the numerator and the derivative of the denominator and leaving it like this, right? So this can work if a couple of things happen, right? If f of x and g of x do not equal 0. So for example, if you end up getting 0 over 0, it's dubious as to whether L'Hopital's rule will work or not. Okay, it is pronounced L'Hopital. It is not pronounced like El Hospital or something like that. This is like a French name, I believe. So do keep that in mind. But if you have something like 0 over infinity or infinity over 0 or something like that, those ones are good. This 0 over 0 is kind of a no-go. It can be, it may work, it may not. So, but the other thing is that the function has to be locally linear. So what do I mean by locally linear, right? Well, if you take like most of the functions that I've shown you in this video, right, like an exponential or a polynomial or a trigonometric function, like sine and cosine specifically, or a natural log, right? If you zoom in, right, and you continue to zoom in on the function, the function approaches a straight line, okay? As you continue to zoom in. For almost every single function that you deal with on a day-to-day basis, this is true, okay? But there are some really weird functions out there that do not approach a straight line as you zoom in. The most common example is fractals, where actually as you zoom in, right, they have a repeating pattern. So like the repeating pattern will be like a zigzag, right? And then like if you zoom in on this part right here, well, it still looks like a zigzag. So you can't apply L'Hopital's rule in that sense because the function is not locally linear, okay? So again, it's very rare that you'll deal with that, but I do need to throw it up there. So, for example, how would we use this, right? Well, we got two polynomials here. We got a cubic and we got a quadratic. If we just try to straight up evaluate the limit by plugging in infinity, we're going to infinity over infinity, okay? So we take the derivative of both sides, and we get a quadratic over a linear, okay? Well, that's still not particularly great because we get infinity over infinity, right? So you might be like, oh, well, we took the derivative. Oh, well. Well, it turns out you can actually continuously take derivatives. You can keep trying, right? So you can keep trying until either you get out something that is meaningful, right? Like this, or if you get some other indeterminate form that is no longer useful, right? So if you end up like taking some derivatives and you get a 0 over 0 at some point, well, then you have to stop, and it didn't work, right? So you can just keep taking derivatives. You can do first derivative, second derivative, third derivative, and you can just keep going as long as you have derivatives to take, right? You do want to be careful not to go down a rabbit hole where, like, if you have a sine or a cosine or something, right? If you keep taking derivatives, well, you're never going to get rid of that sine or that cosine, right? You're just going to keep getting trigonometric functions. So unless you have a polynomial somewhere, it's not really going to help you out too much. So yeah, and like I had the limit sine of x over x, right? The limit as x approaches 0, right? Now, this, of course, is a 0 over 0, right? So it's a little bit dubious as to whether or not you can use it, right? But if you take the derivative, right, you get a cosine of x over 1, right? And if you plug in 0 for cosine, right, you're going to get a 1 over 1, right? So you get 1. So that is a case where 0 over 0, you can't take the derivatives, and you'll get the right answer out. But if you want a more formal proof, again, it's out there. You can go look it up. So next up is multivariable derivatives. So we're probably not going to be dealing with too many multivariable related functions in the next handful of episodes, but I do want to point them out here, just so that you see them, and so when you see them down the line, you're not like, oh my gosh, what is this? So first up is a partial derivative, right? Is that if you have a multivariable function of like x, y, or z, you can take a partial derivative with respect to any variables that are in the function, right? And so how you do this is that you treat the extra variables as constants, right? So if I'm taking the partial derivative with respect to x, y and z are treated like they're constants, right? They're just treated like they're numbers. So how this can play out, right, is if you have some function, we got an x squared times the square root of y plus z, right? Is that if I take the derivative with respect to x, well, I treat y as a constant, so that's why the square root just stays there, right? The derivative of x squared is 2x, okay? And then the derivative of z with respect to x, well, that's 0, right? A constant with the derivative of a constant is 0. If we do with respect to y, again, z is just a constant, so that goes away, right? X squared is still a constant, so that just stays there, right? And you just do the derivative of the square root of y. And then if you wanted to do it with respect to z, well, this whole first part just goes away because that whole thing's a constant, and that's going to go to 0, and then the derivative of z is just 1, right? So to me, this is a good example of showing, like, okay, right, you can take the partial derivative with respect to 3 different variables, and you get out vastly different answers. So yeah. So the next thing that we have is what is called the gradient. So the gradient, again, not going to be used in the next handful of episodes, but will be used farther down the line. But what you have is this thing called the del operator. Okay, and the del operator is a vector. Again, if you take like a calculus 3 class, for example, right, they'll go in, they're like, okay, this is a linear something operator, but this is the definition of it. Okay, is that it's a partial derivative with respect to a variable, and then its associated unit vector, okay? In Cartesian coordinates. I just specify in Cartesian coordinates. If you use a different coordinate system, this changes, which as we get there, we'll cover that. But in Cartesian coordinates, we'll keep it simple. This is what you get out, okay? So if you take if you use the operator on a function, right, you just get a bunch of partial derivatives and then their corresponding unit vectors, okay? And the reason why this is nice is that it points in the direction of greatest increase of that scalar function, okay? So we're going to do this in 2 dimensions, okay? We're going to use the previous example from the last slide. We're going to use this function, except we're going to get rid of z, just to make things a little bit easier to visualize. I tried doing this in 3 dimensions, and then I plotted it, and if you don't know what you're looking at, it would have been very hard to understand what was going on. So, so we have our partial derivatives, right? And so what I ended up doing, right, is you plot the scalar function using a density plot, right? So like low values are dark colored and higher values are lighter colored. Okay. And then so then you plot the gradient, which is a vector field, on top of the scalar field. Okay, so vectors with low magnitude are red, and then vectors with high magnitude are closer to the pink range. So as you can see here, right, is that in the middle, right, our function is near 0, right, and that the direction of greatest increase is straight to the right. It is straight off, it is straight off to the right. Okay. But then as we get farther and farther away, right, since we have these positive, like we have y positive, or we got positive y, we got positive x, right? The direction of greatest increase eventually starts pointing up and to the right, as we go on. So yeah, it's kind of like a curved thing, right? And that's an example of a gradient. How is this useful per se? Again, that'll be future episodes where we talk about applications of the gradient and what it's used for. But in general sense, right, is that it allows you to take a scalar function and turn it into a vector function. So you can go from a scalar to a vector, and you can go from a vector to a scalar. So that's powerful, as it turns out in physics. So yeah, that's coming in a future episode. Next up is the directional derivative. Honestly, not super useful. The gradient tends to be a lot more useful because the directional derivative is just based off of the gradient. Because you just you do the gradient, and then you dot it into a unit vector in the direction that you care about. This does allow me to bring up a key concept, though, of what is called the scalar product or the dot product, where if you multiply two vectors together, you multiply their components, and then you add those things together. So that's one way to do it. The other way to do it is if you know the magnitude of the vectors, it's the magnitude of both vectors times the cosine of the angle between them. And if so like u hat is right here, right? How do you find u hat? Well, you take your vector and you divide it by the magnitude, and you can actually find the magnitude of your vector by dotting it into itself. Okay, and you take the square root. So yeah, so that's the directional derivative. Again, not super useful. I've only ever used it a handful of times. So then the last thing here in the derivative section is we have a total derivative. So what is a total derivative? Well, again, it's not super common that you run into this, at least at the introductory level. As you get into higher and higher physics classes, it'll become more and more relevant. But the idea is, right, is that if you have like a function of a variable and another function, right, you have to account for the fact that y is not just y. Y is again a function of x, sort of like with implicit differentiation, right? Like y is like related to x in some way, so you need to treat it as such. So for example, if you have the function xy, right? If you just did the partial derivative with respect to x, right, you would get y out. Okay, but if y is dependent on x, say that y is equal to x, for example, right? Then this thing becomes x squared, right? And this partial derivative is no longer doing its job. So what you need to do is you need to do a partial derivative with respect to y, and then you need to do the derivative of y with respect to x, and lo and behold, we get what we should expect, and we get 2x. So yeah, it's hard for me again to kind of state why this is useful without using like an example that's too advanced, but you know, here it is for your reference if you're curious, right? You might be wondering, like, well, okay, right? Like in all the other slides, right, we were writing we were writing these, right? And yeah, it just kind of works out. So yeah, kind of just ignore the last 30 seconds of what I said, but yeah, we'll move on to we'll move on to series. So series. Again, right, we're kind of going to cover this briefly because the applications are farther down the line, right? And it's a lot of hand cranking math that, right, isn't super relevant right now, but understanding the concepts can be quite useful, right? So we have what's called a Taylor series, right? And what this allows you to do is it allows you to approximate a lot of functions. I can't say every function that exists, okay, that isn't true, but almost all functions can be approximated as a sum of polynomial terms, okay? So this is the formula, right? And so this is about the point x equals a, okay? So that's why you have all these a's here, right? A can be 0, and if x is equal to 0, then it's called a Maclaurin series, which you see the Maclaurin series of a bunch of functions down here. So like e to the x, right, just 1 plus x squared over 2 factorial plus x cubed over 3 factorial, right? Sine of x, right, it has like this like alternating odd power thing with signs also swapping. Cosine is even powers with alternating signs. And if you're wondering, well, does this have something to do with sine being an odd function and cosine being an even function? The answer is yes. Yes, it does. And then you can have like 1 over 1 minus x, right? That's just 1 plus x squared plus x cubed. So that's interesting. So the idea is that you can take some complicated function and you can approximate it using a sum of polynomial terms. So you might be wondering, well, why is this useful? Well, first let me show you a little bit like a graphical representation of what's going on here. So for example, if you want to take the series of the square root of x, and we want to do that about the point x equals 1, right? You can't do x equals 0, right? Because the square root of 0, right, is kind of an interesting point. You can run a problem, so I decided to play it safe and do 1, right? And I decided to do 3 terms, okay? And so I plotted that, and that function is y, so that is the blue. So the blue curve is so y is the blue curve. And then I did 11 terms, right? So z is 11 terms, and z, it turns out, is green, so z is a green one, and then our original function is red. Okay. The idea is that the more and more terms that you add to your approximation, the better and better it is. As you can see, that square root of x is a little bit of an interesting case where, for some reason, it just like spikes up here, right? And that, and as x goes to infinity, the 3 power one actually is better, which is interesting. But I can tell you that from here to like right about here, the 11 term function is going to be a lot better. So in general, the more terms you have to your approximation, the better it's going to be. So if we go back here, right, there's like a range as to where these are valid, right? That's convergence. Yeah. Again, this is why I take a calculus class. They'll teach you about convergence. They'll teach you about these convergence tests. They'll teach you how to use them and when you need to use them. I mean, in physics, we use these on a case-by-case basis. If we have a reason to suspect that our approximation may not be valid in a certain region, we'll run a convergence test. But most of the time, we're using known stuff. So rarely you have to use this in a physics setting. But in a math setting, yes, you do have to prove that these series converge over all x or over a certain range or converge to the function itself. And that isn't something that I want to show. So go take calculus if you want to know more about convergence. So as I alluded to earlier, why is this useful? is that it can approximate difficult functions to make them easier to use, right? Is that it takes something complicated, for example, like 1 over 1 minus x, and it turns it into a polynomial, right? And when we do example problems, you'll see why this is really powerful, okay? But this is also how your calculator works, right? Is that a polynomial, right, is a series of addition and multiplication, right? And your calculator is very good at doing addition and multiplication extremely fast, right? And so it actually, it's like when you plug in sine of a value, it doesn't evaluate it as sine of 45 degrees. It plugs in that 45 degrees or pi over 4 into the Taylor series expansion, and it gives you a number. So yeah, that's why it's useful. Is it allows your calculator that you probably hold so close to your heart to function properly. So the last piece that I'll mention is Fourier series. So we use polynomials in Taylor series. Fourier series uses sine and cosine to approximate functions. You might be wondering, well, why would I use sine and cosine if I could use a polynomial? Polynomials seem a lot nicer. And the answer is, well, cosine and sine are waves. So if you have a wave-like function, sine and cosine are going to be better at approximating that. So I'll probably do a more in-depth episode to this way down the line when we actually need to use Fourier series. But just so you have the information, this is how you figure out those constants that are in the formula. Right, if you wanted to use a Fourier series to approximate y equals x, right, with varying different amounts of terms, right, you can see that the more terms you add, right, like the green wave is a lot better than the blue wave, for example, right, and our function is in the red. And then, like, if you have a sawtooth wave, right, again, a periodic function, right, like it does a pretty good job of approximating what's going on here. But if you try to use a polynomial to approximate this, yeah, it's not going to happen. It's not going to be very efficient. So there's that. So we got some problems to do. What I'm going to do is that since I'm trying to cut down on the length of these episodes, I'm actually going to call it. I'm going to call it right here. So in the next episode, I'll go over a few example problems. So with that being said, if you enjoyed the episode, please leave a comment, please subscribe if you enjoyed. I'm also always looking forward to hearing your feedback. So feel free to drop a comment. You can also shoot me an email. The email will be in the end title screen. So thanks again for watching, and I will see you in the next episode.